Hello everyone. Today we're going to wrap up abrasive machining. We're going to talk a lot about grinding, different kinds of grinding machines, in-feed, plunge cut, and crete feed mainly. So in-feed, you're going to feed the grinding wheel into the part, and then you're going to move the wheel around the part. Plunge, you're going to feed the wheel in radially and rotate the workpiece. So centerless grinding would be kind of plunge cut. Surface grinding would be kind of an in-feed grinding. Crete feed's pretty rare. We'll talk about that when we get there. So this is a cylindrical, like a tool post grinder, something like that, where I've got the part that I want to grind. I'm going to turn it slowly, either between centers or chucked or something like that, or even centerless. Then I've got a grinding wheel here that I'm going to turn as well, and I'm going to remove material by abrasive machining the outside diameter of this thing. So if I want to finish a shaft down to a 1/10 of a 1,000th of an inch or so and get a really good surface finish for like a bearing press or a race for where a needle roller bearing needs to rest, something like that, grinding is the way to do it. Or if I need to do some finish machining on a piece of really hard steel that I've just hardened, this is a good way of doing some finishing passes on that too. That's a pretty common process with high strength steels, where you do most of your machining in an annealed or normalized state, and then you'll heat treat it and then grind it. Heat treating, you're almost always going to mess up your surface finish to some extent, and you need to leave a little bit of a tolerance, a few thousandths to grind off, and then you use a grinder on the critical areas to remove the excess material and finish it. I think pretty well everything on here is covered to some extent. Specialty grinders for grinding crankshafts and camshafts. So those cams have, they're not just a concentric circle, and crankshafts will have offset journals for the connecting rod bearings. You'll need specialty grinding machines for those. But if you're making engines, there's very few people that have the equipment to make engines. So the people that do make engines can afford the specialty grinders. For everyone else, it's hard to do that kind of stuff. Grinding machines. So chucking, centerless. We'll talk a little more about centerless, planetary, surface, conventional. We'll talk a little bit about crete feed, tool grinders, things like that. Disc, contour and thread, bench and pedestal. There's different kinds of grinders. Everything from a bench grinder in your shop to these really big centerless grinding machines. So what is centerless grinding? Centerless grinding, you have two wheels. You have the workpiece between them. The wheels are different size. That causes the workpiece to rotate. They're going to be at different angles, and that allows the workpiece to be fed in automatically as the wheels rotate, depending on what that angle is. And this is going to, so if you need to like take an extruded steel pipe and make it a really nice consistent round diameter, centerless grinding works for that. If you need to take like hot rolled bar stock, which has a really gross surface finish, and make it nice and true and concentric, you can use centerless grinding for that. A lot of terminology here, and not a lot of it's that necessary or interesting. The main thing to know is you've got two wheels. They're going to be, the axis of them is going to be tilted a little bit. You put the part in there. The predominant force needs to be down onto the rest for this to work. Otherwise, it's going to get shot out. Bad things are going to happen. So you need some kind of a rest of some type, and you need the forces predominantly down to keep the workpiece put. So here's a big picture of a centerless grinding for grinding these little blanks through here, and you just get them started in there. They run through, and they're nice and ground on the way out. Pretty common process. Again, I'll link the videos in the description. So advantages: it's fast operation. It's a pretty skillless operation. You just feed parts in, they get ground. It can be pretty easily automated. You can take a pretty heavy cut due to the way that the part is supported. You can get very good size control on it. Very repeatable size control too. With a sufficiently big grinding wheel, like these big giant grinding wheels here, they don't wear very quick. You could automatically dress them as they grind. You could have a dressing wheel somewhere on the back side of it to keep them dressed so that they cut true and can run quite a long time. It's a special purpose machine. You got to have round things. That's the problem, right? Flats, keyways, things like that are going to cause problems. So it needs to be round. That's the biggest downside. Grinding tubes, there's no guarantee that your ID and OD are concentric, but that might be an issue. You might get a thin spot in the wall of a tube. Working on parts with more than one diameter is an issue. This horizontal grinding, spindle grinding, that's probably the most common kind of grinding in a machine shop that's not like bench grinding. The most kind of a machine grinding would be a surface grinder like this, where you've got a spindle that rotates, you've got a grinding wheel here, you've got a part. Now usually you're grinding ferromagnetic materials, mainly steels and irons. We talked previously, you don't grind aluminum. Aluminum doesn't grind very well. It loads up the tool, it might get hot and the tool might break, the wheel might break, and you might have problems. There's some applications where you can get around that, but for something like surface grinding, you're not going to surface grind aluminum in most situations. I've never done it. I've never seen it done. Again, it's such a thing. They're so rare that these machines will usually have a magnetic vise and nothing else. No other way of connecting the part to the base. So again, they just assume you're doing steels or irons. So anyway, there'll be a magnet. Magnet holds the thing you want to grind. You'll take very light, very shallow depth of cut passes, and then you'll basically feed down. The machine will usually automatically step over and feed back. These things can usually run a full. They're set up so that once you do, you can do for each first cut setup. It'll sweep back and forth at your first depth of cut. You'll feed in downward a little bit, or feed the table upward a little bit, and then start it again, and then the machine will automatically run through, sweeping back and forth. Even the dumb old mechanical ones will pretty well do, at least the back and forth part of it will be automated, and the step over usually is automated as well. So here's a surface grinding machine. Again, you've got a magnetic vise that's holding it's not really a vise, it's just a slab that's magnetic that holds your workpiece. You've got your grinding wheel here. In this one, you move the grinding wheel up and down. This one is a CNC machine. Again, even the mechanical ones, so usually once you get it set up, it'll do the X and Y motion for you. It just sort of does the back and forth with a step over. This one's full CNC, so it can do the Z moves for you as well. It's a fairly slow process. If you need to remove a lot of material, this can take a really long time. So you really want to leave just a few thousandths ideally before you get moved to grinding. Any more than that, you probably should have machined it off. Horizontal spindle rotary tape. Rotary table. My voice is starting to go for the semester. This always happens at the end of the academic year. So here, if we've got lots of little widgets that we need to grind the top of it, this works. Very quick method. You probably have some kind of magnetic chuck again, because we're mainly grinding iron, steel here. Vertical spindle reciprocating table. Right, this we don't need any cross feed again. We're grinding a whole lot of widgets, or one really big widget. You can imagine these machines are expensive and big. This is a 415 horsepower grinder. That's a lot of power. That's a whole lot of power. That's actually a scary amount of power in an industrial machine like this. So that's for doing a lot of grinding on a lot of parts, or one really big parts. It looks like they're doing pretty thin plates that they're grinding here. Vertical spindle rotary table. It's called Blanchard, where I'm rotating the grinding wheel and I'm rotating the parts, and I get this kind of nice characteristic Blanchard ground surface finish. So this is a 250 horsepower Blanchard grinding machine, and I can put a 129 swing on that. So if I need to grind something really nice and really gigantic, this is the machine to use. Crete feed. So I've not done crete feed machining. I've never seen it done before. So I'll just go over the slides. I don't have any personal anecdotes to add to this, but it's kind of interesting. We do the entire cut in one pass. So instead of a lot of small, shallow passes, we're going to do, instead of cutting a thousandth or two, we're going to cut an inch off. And instead of moving at a pretty fast speed, in all of these, the relative speed of the grinding wheel versus the part's pretty high compared to conventional machining. Since we're increasing the depth of cut by 1,000 times, we're going to reduce our feed by 1,000 times. So we're moving very slowly. So we're moving a very aggressive cut, very slow feed rate. This is going to be, it's a lot of force, a lot of power, a lot of heat. Uh, and there's a lot of issues with this, but for some things like deep slots or cutting complex profiles and really hard to grind materials, this might be attractive. So yeah, for regular surface grinding, we're going to take really shallow, lots of really shallow passes. In creep feed, we're going to be taking big, gigantic passes here. Now, as you can imagine, this is really going to wear your wheel down. So you need to continuously dress the wheel and true the wheel as it runs, and you need a lot of coolant to keep this thing from getting too hot. Again, never seen it. So it's specialized machinery. It needs to be very strong. Needs variable spindle speed. Most machines have variable spindle speed. Very low range table feed. That would be different than a normal grinding machine. A lot of power, a lot of coolant, flood coolant for sure. And then you need some kind of continuous dressing and truing of the wheel. Not just dressing, you'd have to true the wheel too. Honing. So honing is an abrasive process for removing a very small amount of material and maybe putting a specific surface finish. Like in honing cylinders, you try to put this crosshatch pattern that helps the rings seal. Without that crosshatch, the rings don't seat very well, and they don't seal. You don't get good sealing on the cylinder over time. So they make these little stone hones like this. This is for removing less than 5 thousandths, and it's usually a lot less than 5 thousandths. Usually it's like a thousandth, maybe at most, or two. So really a lot of these you're just trying to touch up the surface, remove any high spots, put the cross hatching back in. But there's honing for non-engine things too, and again it's the same thing. You basically use an abrasive stone like this. Think about like knife sharpening. You're essentially honing and removing just a little bit of material to restore the blade's edge. You just a few thousandths. Different abrasives for this, conventional like aluminum oxide and silicon nitride. Diamonds, obviously industrial diamonds, synthetic industrial diamonds, cubic boron nitride, etc. Obviously, the harder that abrasive, the more expensive it's going to be. But the harder materials you can machine as well. Stones from 80 to 600 grit. They make even higher than that. There's all sorts of weird Japanese knife sharpening videos on YouTube, which you can go on a side and find, where they're using like 5,000 grit stones or something silly like that to finish knives. And that's great. It's good for videos, but finish that good, the knife edges, the very leading edge is going to be so fragile that it's probably not going to stay that sharp for very long. So there's sort of a practical limit on where you want to go with honing stones. Unless you want to sharpen your knives a whole lot. There might be some added compounds to modify the cutting action. You might need to use some kind of an oil or water, something like that. If you need a specific surface finish, like they make these little ball hones for cylinders. These aren't good for removing material. They're good for putting the cross hatching back in a cylinder. So they make these little ones for like hydraulic cylinders, things like that. They make ones like this for engines. They're only going to work for a very narrow window of bore diameters. You got to watch that, but they're really good for cleaning up the surface finish. But you might not end up with a flat surface like you would with a nice stone hone like this. They make big honing machines like, this is an engine block here. We're honing the iron or steel sleeves in this thing. Again, so the block might be aluminum. A lot of engine blocks are aluminum now. You're not going to hone aluminum. Same reasons you're not going to grind aluminum. This machine, though, you're honing the actual steel liner in here. And even like there's some aluminum blocks now. Like Ford's got a process for depositing a very thin layer of iron onto aluminum where they basically vaporize a metal wire. And when the wire vaporizes, it expands out and little particles of iron embed. You do it in an inert environment. It's like basically imagine a MIG welder where you turn the power up and have it completely surrounded by an inert gas. The wire essentially vaporizes, but there's no oxygen, so it doesn't burn. And little particles of iron fly in all directions and hit the wall of the cylinder and leave a really thin layer of iron. And then you go through and hone it, and you've got an engine. These actually have steel sleeves in there too that may or may not be replaceable, but they're thicker sleeves, so you can make the cylinders, the bores a little bit bigger with that spray bore process. It's pretty cool. Don't know how long. Actually, I think I had a car that had it. I can't remember what all they put that in now, but it seems to last pretty well. I just don't know about remachinability. But anyway, hone machine like this machines bores, or does the honing process. And gets the feed up and down, and the RPM synced up, so you get the nice cross hatches you want. Again, I'll link the videos. Fine grinding and super finishing. Really high grit stone with a lot of a full film of lubricant of some kind, just for removing high spots. That's essentially all you're doing with fine grinding. You just really taking the top of the high spots off with fine grinding. Flat honing, using a super abrasive solid or pelleted plates. And you're going to use a lot of coolant for it to carry away all the particles. And again, I don't know about this, often do not require cleaning. Eventually if you're removing material, you're going to need to clean at some point in time. Now, if you're just removing the high points, it might be a really long time before you need to clean off the material, but at some point you will. Again, there'll be a video here that I'll link. Lapping. So this is the last finishing operation. So this is where you have fine abrasive particles in a soft material. So polishing would be a kind of lapping. So you have a soft material called lap, which can be a cloth wheel, even cast iron for hard materials. You might have really hard, like a silicon nitride or cubic boron nitride or diamonds embedded in cast iron for a lap. Copper or some soft material relative to whatever it is you're trying to lap. And then you're going to have an abrasive carried in that. And you're going to have some kind of abrasive, some kind of lubricant, like grease, oil, water, something like that, or wax for grinding. And you're removing very small amounts of material, less than 1,000. You probably shouldn't try to remove 1,000th in lapping. That's something that grinding can get you down to 1/10. Lapping, you're talking about past that. So you really should do machining until you're at the limit of your tolerances on that, your practical limit, and then grinding down to your practical limit on that, and then some kind of a super finishing or lapping operation past that. It can be used on metals and non-metals, glass, lapping on lenses, things like that. It can be done manually or with machines. Again, on metals, this is really in polishing. You've got a cloth wheel, you've got a buffing compound that has a very fine abrasive particles in a soft material, which would be some kind of wax usually that also acts like the lubricant, and you can remove very small amounts of material and get very high quality mirror surface finishes on a lot of materials. It works on aluminum, so we can't really grind aluminum, but you can polish aluminum to a mirror polish. But what you're doing in this, and why you can polish aluminum but you can't really grind it, is the problem with aluminum is it loads up the wheel. Here your abrasive is in a soft material that gets basically you basically charge up the wheel for polishing. You charge up a cloth wheel with the abrasive, and it doesn't matter. There's really nothing to load up. Your abrasive is essentially used once and then flung off somewhere in the shop, and you don't have anything to load up like you would with a grinding wheel or something like that. And here's a lapping machine where we have the part we want to hold here, and then we'd have some soft material here, and then we'd use a lapping compound applied to that. And here's a bigger one here. Free abrasive, ultrasonic, water jet, gas jet. Water jet's the most common of these, I would say. Ultrasonic, I've not ever seen. I've seen ultrasonic cleaning, but ultrasonic abrasive, that's something I have not seen. You've got grit and some kind of a slurry in almost all of these. And it works. It's an effective use of low-cost abrasive. Like with water jet cutting, you can do a lot of your cutting with aluminum oxide, and it's really common. You're not sitting there depleting a whole bunch of little diamonds or cubic boron nitride. So you can do a lot of work with a fairly cheap abrasive. You usually have continuous flushing of abrasive material too. That cools things down, prevents wear, prevents a new edge. I don't know about this, like for water jet cutting. You're really using your abrasive once in that, so it doesn't really matter what's happening to the tool because your tool's expendable. Ultrasonic machining, I've not seen this, but essentially you've got a tool You're going to shake it at high frequency, somewhere on 20 kilohertz, which would be like the upper limit of what a young adult human could hear. I can't hear to 20 kilohertz anymore, so this would be almost silent for me. Those of you that are taking this class that are like 20 years old, you can probably still hear this if you haven't killed your hearing. And it'd be really, really annoying, I would imagine. But anyway, you've got this tool shaking somewhere 20 kilohertz. You've got a slurry that goes in here, and you're going to wiggle that slurry around and remove a little bit of material in here. So for machining really, really hard things or brittle materials that might break from conventional grinding, this might work. Water jet machining, really common, really cool. Especially at S&T, we do a lot of water jet machining. If you're on a design team, you've probably done a ton of water jet cutting. You guys are familiar with it. If you're not, you can understand the concept. We take water at tens of thousands of pounds per square inch. We introduce an abrasive. We have some kind of guide for it. I guess that's really up there in the nozzle. And the nozzle has to be incredibly strong. So some kind of a gem, which sapphire would be. I think sapphire is aluminum oxide. I believe it's corundum, which is basically the same as the abrasive, but the abrasive doesn't touch it. If the abrasive was up here, that nozzle would not last any amount of time. So here, this is just resisting water. So the water impinges on the abrasive flow, and it shoots this stuff all out the bottom, and essentially is a grinding operation. We got very high speed of the abrasive particles, somewhere around 3,000 feet per second. So it's quick. I wonder if there's a shock. Surely there's a shock wave somewhere, because that's faster than the speed of sound. I don't know. That'd be interesting to think about the aerodynamics of this, and if there's shocks, since that's traveling so fast. That'd be, I don't know. That's kind of interesting. But anyway, jet's pretty small, 3 to 20,000, something like that. So you have to leave a cut allowance. It does widen out quite a bit for thicker materials, and you have to allow for that. You might need to go through and do a finish machining operation for thicker parts. And you can cut a lot of things, right? You can cut the hardest steels, aluminum, rock, granite, all sorts of interesting things you can cut with water jet. And you use generally fairly cheap abrasive, aluminum oxide. Abrasive jet machining, we're using inert gas instead of the water. I'm not familiar with that at all. I mean, I don't know if this diagram's even right, because it's got water going in there. It would seem to me like that's just a water jet with gas. I don't quite get it. So I don't know much about this abrasive jet machining. But water jet, I've had a lot of parts water jet before, and for sheet metal, small production runs of sheet metal, it works really well. Laser's a little faster, a little cleaner, but there's some stuff that you can cut with a water jet that you can't cut with a laser, and it's a lot cheaper. For cutting power to cutting power, a water jet's going to be probably somewhere around an order of magnitude cheaper than, maybe not quite, but cheaper than a laser. High-powered multi-kilowatt lasers are expensive things. 60,000 psi is a lot, but it's like a modern diesel has a high-pressure pump that pumps around 36,000 psi, and they make those pumps, and they're a few $1,000s. So that's actually an interesting question. You could probably take a diesel pump and maybe modify it to make a water jet machine. The only problem is that you're designed to run diesel, which is a lubricant in and of itself, and if you just replace it with water, the pump's going to die probably pretty spectacularly. But that would be an interesting project to try. But anyway, that's a pressure that's attainable with modern technology fairly easily. So it's fairly low tech compared to laser cutting. Laser cutting multi-kilowatt lasers are not a low-tech thing. They're not something you could just grab some part off the shelf and kind of kludge together like you could do with a water jet. I've seen some really interesting homebrew water jet machines, so I have a feeling water jet's going to get cheaper. It's probably 20 years is how long this has been in common use, and maybe a little longer than that. That's how long we've been doing a little longer than that here at Rolla. But it's something that I see getting cheaper, because there's really no good reason for it to be as expensive as it is, because the XY motion, that's really cheap, and they've got that done in 3D printers with the XY and Z motion. That's cheap. We're talking a few $1,000s, maybe 10,000 for a really good XY table. Again, the pumping guts, that's something that is again, there's no reason for it to be as expensive as it is. So I see that going down and being more accessible as time goes on. So that's it for today's lecture. Thanks everyone. I'm not gonna upgrade iTunes, so that's it for today. See you.